The overall context, our starting point, is the time-independent Schrodinger equation. We have this generic expression for the Laplacian, which is related to the momentum, in this case related to the kinetic energy. So this is true in any coordinate system, whether it's one-dimensional, two-dimensional, three-dimensional, etc. If we express this Laplacian in spherical coordinates and make our usual separation of variables guess, namely that psi of r, theta, and phi is going to be equal to some function of r times some function of theta and phi, we saw in the previous lecture that for potentials that are only a function of r, as we're considering in this case, the angular part here, y of theta and phi, actually gave us spherical harmonics, y Lm of theta and phi, as our solution. The radial part was a little more complicated, since that's where the bulk of the interesting derivatives are in the Laplacian. And if we make the substitution u is equal to r times r, I should write it the other way around, r the coordinates times r the function of r, so this is now u as a function of r, we ended up with this as our radial equation as a result of separation of variables. You can see this in the previous lecture on the discussion of the time-independent Schrodinger equation expressed in 3 dimensions. In the case of the hydrogen atom, we have a very specific form for the potential here, namely that V of r is given by the usual equation from electrostatics, minus e squared over 4 pi epsilon naught 1 over r, where e is the electron charge, pi of course is pi, epsilon naught is the permittivity of free space, Coulomb's constant essentially, 1 over 4 pi epsilon naught. So this is our potential energy. In the case of a proton being orbited, and I really shouldn't draw this, especially in a quantum mechanics class, being orbited by an electron, the distance separating the proton from the electron is what determines the potential energy. And we have a minus sign here to imply that as the electron approaches the proton, it's actually losing potential energy, meaning it would be gaining kinetic energy if we were letting it fall into towards the nucleus. It's attracted to the nucleus, essentially. That explains the minus sign. So that's the potential function we have to work with. We can make this a little bit easier to work with if we make a change of variables. So the equation we have now, the radial part of the Schrodinger equation, expressed in terms of this redefinition u is equal to the actual radial function times r, we have a couple of constants, and we can rearrange the constants. For instance, we're going to do this by dividing through by the energy, dividing through by E, and we're going to make our usual definition of a constant k. K squared is minus 2me over h bar squared. The minus sign here refers to the fact that for bound states in this potential, which, looks like a potential well, we're going to have bound state energies that are negative. So if energy is negative, k squared is a positive number. There's no real problem with this. If we make these definitions and we make this simplification dividing through by E, we end up with 1 over k squared times the second partial derivative of u with respect to r squared. That's coming from this term. And that's all equal to, now rearranging some terms from the left-hand side to the right-hand side of the equation, 1 minus m e squared over 2 pi epsilon naught h bar squared. And I'm rewriting this a little strangely. There's a k here, and then there's a kr, 1 over kr, plus l plus 1 over kr squared. And this is all acting on u, or multiplied by u in this case. So we just have our second derivative term. That's been moved to the left. The h bar squared over 2m has been taken care of. When we divide through by e, we've got 1 over 2me and h bar squared, so we have a 1 over k squared. The dividing through by energy means we've just got u on the right-hand side here, so that contributes this 1. Our array of constants here with an overall 1 over r sort of behavior is what we get from this term, which still has its original minus sign. And the h bar squared over 2m e again gets us a k squared r squared in the denominator in this term, with the usual ll plus 1 on top. So this pretty clearly suggests that we should make some change of variables. We have these kr's, which always sort of appear next to each other. So let's make the change of variables rho is equal to kr. If we're going to re-express this as a function of rho, we need to define a new function, which I'll temporarily call w, as a function of rho. And by that I mean w of kr. I'm just going to say w of rho is u of r. So I'm re-expressing my function, except in terms of rho instead of r. We can then, using this definition of w, do things like calculate derivatives. For example, if what I want to know is the derivative of u with respect to r, since that's going to appear, for instance, in the second derivative here, the derivative of u with respect to r is equal to the derivative of w of rho now, with respect to r, which we can just evaluate by the chain rule. If I want to differentiate a function of rho with respect to r, first I differentiate with respect to rho, and then I multiply by the derivative of rho with respect to r. The derivative of rho with respect to r, of course, we know what that is. This is just k. So this is going to be k dw d rho. I shouldn't write p's, I should write rhos. Now, Griffiths takes some liberties with the notation here. He doesn't define a secondary function w. He leaves this in terms of u, implicitly treating u now as a function of rho instead of u as a function of r. I'm going to stick with his notation in spite of the fact that I find it a little confusing. I find it much easier to make changes of variables here if you change the function in addition to the variable. But overall, you can see what's going to happen here. I'm going to, instead of rewriting this in terms of w, I'm just going to rewrite it again in terms of u. But now, the second derivative of u, really w, with respect to rho is going to be given by expressions like this. And you can see for yourself, if you do the chain rule again here, you're going to end up with another factor of d rho dr. So we're going to end up with a k squared, appearing in front of our second derivative of u with respect to rho. So the second derivative of u with respect to r is k squared times the second derivative of u, i.e. w, with respect to rho. So the k squareds are actually going to cancel out. That's the purpose of doing this sort of change of variables. Our re-expression of u as a function of rho means we can sort of fold the k here in the denominator in with the dr, turning it into a d rho. When you do that, the final equation you get is second derivative of our new u function of rho with respect to rho is equal to 1 minus, and I'll define another constant, rho naught, over rho, plus l plus 1 over rho squared, all multiplied by u. And this constant rho naught absorbs the complexity in this. Rho naught is defined to be m e squared, sorry, not m sub e, m times e, the electron charge, squared, divided by 2 pi epsilon naught h bar squared k. So we've defined some constants and we've made a relatively straightforward change of variables. And we end up with this as our equation. This is the equation that we're going to want to solve, and the approach we're going to take to solving it is going to be very similar to the approach that we took when we were working with the quantum harmonic oscillator in one dimension. We're going to, in the end, use a power series to solve this equation. But before we use a power series, it's good to think about what the solutions to this might look like for very large or very small values of rho in this case. If there are problems with those asymptotic forms, for instance, if the function blows up or if the function does something poorly behaved, it's going to be very difficult to represent it with a power series. So if we can somehow factor out or simplify, much along the way of separation of variables, those asymptotic forms, we may be able to simplify the expression here, or at least derive a simpler equation, or at least an equation which has simpler power series solutions. So let's take a look at what those asymptotic forms are. The first asymptotic form that you might think of is, let's see what happens when rho goes to infinity, i.e. very, very large rho. Well, if rho is very, very large, rho naught over rho is going to be very, very small, And L plus 1 over rho squared is going to be even smaller. So really the only relevant term we're going to have in our equation for u with respect to rho is this 1. So the equation we're working with is going to be second derivative of u with respect to rho is equal to u. Now, second derivative of a function gives you the function back. You know that sort of function. You know the solution to that. The general solution to that differential equation is u is a e to the minus rho plus b e to the rho. Whenever I take the derivative of an exponential like this, I essentially am leaving the function unchanged. This is just the original exponential. The first derivative of this term gives me a minus sign, but since I'm taking the second derivative, I'm going to get two minus signs, and I'll end up back where I started. So these are the sorts of solutions that you would expect for this ordinary differential equation. Now, since what we're looking at is rho going to infinity, this term behaves itself rather poorly. For very large rho, this term blows up. So we can't have that be part of our solution. If we're going to say b equals 0, then the solution that we're working with is just u is a e to the minus rho. That's one asymptotic form. For very large rho, we expect our overall solution to look like a decaying exponential. Keep that in the back of your mind. The other limit that we're going to work with is rho goes to 0. When rho goes to 0, this 1 is going to become utterly insignificant compared to 1 divided by 0, or 1 divided by 0 squared. If rho is a very small number, 1 over rho squared is going to be much, much larger than 1 over rho, is going to be much, much larger than 1. So this is the dominant term for very, very small rho. That means the equation that we're working with here is the second derivative of u with respect to rho is equal to L plus 1 divided by rho squared u. This should also look familiar to you. I take the second derivative of a function of rho, and I get the function back divided by rho squared. Now, if I told you the first derivative was the function divided by rho, and the second derivative was the function divided by rho squared, you should think along the lines of polynomials. For instance, suppose I took x to the n just as a function of x. If I differentiate this with respect to x, I'll get n, x to the n minus 1. If I differentiate with respect to n, again, I'll get n times n minus 1 times x to the n minus 2. And I can, of course, rewrite this as n minus 1, x to the nth, all divided by x squared. So this is the sort of behavior you would expect from a polynomial. It doesn't work for just any order of polynomial, though, because we have this constant here, and this constant has to somehow be analogous to the constants we get from the differentiation. If you go through and actually work out what the allowed values for n are under these circumstances, it turns out there are two of them. We end up with our general solution here being u is c times rho to the L plus 1, and the alternate solution is d rho to the minus L. Both of these will give me an L plus 1 and an L. This one will give me the L plus 1 first, and then the L when I get the take the second derivative, and it will give me my original function back up to the reduction in the power of rho by 2, which you can take care of by dividing by rho squared. Whereas this term gives me a minus L, and then a minus L plus 1. So again, L plus 1, the minuses cancel out. And I've, again, reduced the power of rho by 2, which you can take care of by dividing by rho squared. So this is a legitimate solution. In general, however, what we're looking at is rho very, very small. And when rho becomes very, very small, rho to the minus L, where L is what we got when we were talking about separation of variables in the theta direction, we ended up with, L is going to be a positive integer. So we're going to end up with something that blows up here as well. That means is that d is going to be equal to 0 in our solution, and our general solution then is just going to be c rho to the L plus 1. So those are the sorts of asymptotic forms that we expect to get. If we combine these together, what we're going to do is guess that my original function, u, expressed as a function of rho, I'm going to guess that I can simplify this by writing it as rho to the L plus 1 times e to the minus rho times some new function v of rho. And I hope to derive a differential equation for v of rho that is somehow more simple, or at least easier to represent with a power series than this original differential equation. So, did all of that help? Is this gas going to work? Well, the equation that we have to work with here has second derivatives of u with respect to rho. So we're going to need to take some derivatives. So, du d rho, let's start there, is going to be the derivative with respect to rho of our guess in terms of v. U of rho given by rho to the L plus 1 times e to the minus rho times v, our function of rho. Well, we have three terms in this equation, and we're going to have to use the product rule to evaluate this derivative. So first of all, I can let the derivative act on the rho to the L plus 1, and I'll get L plus 1 times rho to the L. The other two terms will be untouched, e to the minus rho v. Next, I can let the derivative act on the e to the minus rho. That's just going to give me e to the minus rho back with a minus sign out front. So what I'll get for that term is is rho to the L plus 1 untouched times e to the minus rho times v with a minus sign from the differentiation. Finally, I can let this derivative act on the v, which will leave the rho to the L plus 1 and the e to the minus rho untouched. And what it's going to give me for v is just, well, the first partial derivative of v with respect to rho. Since I don't know anything about v, I can't simplify that. But that's all right. That's what we're going to have for the first derivative. For the second derivative, you can, well, repeat the procedure. Sorry for the messy notation. This is L plus 1 here. The second derivative, you can imagine taking, again, the derivative with respect to rho of all of this. And I'll spare you the details. It's again going to involve the product rule, applied to this term, and then applied to this term, and then applied to this term. The second derivative of u with respect to rho, which is what we need for this equation, is going to be equal to something complicated, but I'm skipping out here. And finally, at the end, after doing a little bit of simplification and rearrangement, rho to the L, e to the minus rho, times this big long expression, minus 2L minus 2 plus rho, plus L plus 1, over rho, times v. We end up with something that doesn't have any derivatives applied to v, just from the derivatives applied to the other terms, the terms other than v, in these product rule type calculations. We also end up with terms that have first derivatives of v from only allowing one of the two partial derivatives to act on the v of rho. And those terms end up looking like 2 times the quantity L plus 1 minus rho times just the first derivative of v with respect to rho. And finally, we have terms that have a second partial derivative of v with respect to rho, and that's what you get if you make both partial derivatives in the chain rule, or in the product rule, act on the v, leaving the other two terms untouched. And in this context, since I factored out a rho to the L e to the minus rho, that term is rho, and that's it, there's no e's, sorry, rho times second derivative of v with respect to rho. So that's our expression for the second derivative. It becomes our new left-hand side. So let us rewrite all of this, and I'm going to use a little studio magic here, which may or may not work. I'm going to copy-paste that expression, and then I'm going to shrink it down so I have some space to work with. So this expression is just reappearing here. This is our new left-hand side. And it's going to be equal to, well, our right-hand side, same as before. Not much is going to change about this. 1 minus rho naught over rho plus L plus 1 over rho squared times u, which we've re-expressed in terms of rho to the L plus 1 e to the minus rho v. So, let's see how we can manipulate this. This had better simplify quite a lot, or we've wasted our time. First of all, we have an e to the minus rho on the left-hand side and an e to the minus rho on the right-hand side. So we can cancel those out, just dividing through by e to the minus rho. Second of all, notice that we have an L plus 1 over rho times rho to the L. Whereas here we have an L plus 1 over rho squared times rho to the L plus 1. Here we have an L plus 1 minus 2 for the total powers of rho that are multiplied by this term. And here we have a rho to the L minus 1. These terms, this term and this term, are actually going to be the same. You can see that if you actually expand these things out, but I'm trying to save time and I'm trying to save space. So if you actually expand these out, this L plus 1 over rho and this L plus 1 over rho squared ends up canceling out because of the way the powers of the rho outside the expressions end up working out. So that's all well and good also. Finally, we have a 1 here multiplied by a rho to the L plus 1 and a rho here multiplied by rho to the L. Those are also going to cancel out. Since, if we actually expanded them out, they would have the same power. This would be rho to the L plus 1. This is going to be rho to the L plus 1. So we've lost this term as well. Finally, you'll notice that we have rho to the L plus 1, and we have an over rho here. You have a rho to the L, and that's all. So we're effectively, if I multiply in one of the rows from this rho to the L, I'll be able to cancel this 1 over rho out. Then I'll just have a rho to the L here and a rho to the L here. I've gotten rid of the other two terms in the square brackets here, so I can cancel out the rho to the L as well. What you're left with when you've done all of that for our overall partial differential or ordinary differential equation for v is that rho times the second derivative of v with respect to rho, and I'm rearranging terms, moving things to the left-hand side so we have something that looks more like a typical ordinary differential equation, 2 L plus 1 minus rho, what we're left with from the right-hand side, from the left-hand side, multiplied by the first partial derivative of v with respect to rho. We weren't able to cancel anything out having to do with first partial derivatives of v, since of course there aren't any of them on the right-hand side, plus rho naught minus 2 L plus 1 times v. And that's all equal to 0. So this is what we get for our simplified ordinary differential equation now for v. Did this actually help? Well, you'll see actually that it did. The reason this is a useful thing to do is if you look at our original differential equation here, while it took a lot less time to write this than it does to write this much longer expression, we have a rho and we have a rho squared here, whereas these rows in the denominator don't appear in our final expression. That's because the rows in the denominator, for instance, those were relevant when we were considering the rho goes to 0 limit, and we factored out the dominant asymptotic behavior for the rho goes to 0 limit with this rho to the L plus 1 guess. So the rho to the L plus 1s ended up canceling out the 1 over rhos in the denominator here. The 1 also ended up canceling out, and that was what gave us the e to the minus rho asymptotic term. So we don't have terms that look like these sorts of constants multiplied by u anymore, which is good. We now have something that we can work with in the context of power series. So let's go ahead and do a power series solution to this differential equation. The power series solution that we're going to use is the same as power series solution that we used in the context of the quantum harmonic oscillator. We're going to guess that v of rho can be expressed efficiently by a sum from j equals 0 to infinity of c sub j rho to the j. This is our guess. We can substitute that guess directly in for the v here, but we also need a first derivative and we also need a second derivative. So let's go ahead and calculate those derivatives. The partial derivative of v with respect to rho, using this power series representation now, is going to be given by the sum from j equals 0 to infinity of j c sub j rho to the j minus 1. If you're confused about how this happens, think about expanding this sum out, actually write out the first few terms of this sum and take their derivatives, and you'll see that this actually works. I can also rewrite this, relabeling the index of the sum, essentially replacing j with j plus 1 everywhere here and replacing j with j minus 1 in the limits of the sum. What you end up with under those circumstances is the sum from j equals 0 to infinity contains the only relevant terms, j plus 1 times c sub j plus 1 times rho to the j. I'm rewriting the sum here because it's useful to have an expression for the first derivative of j that I can use that has a rho to the j in it. Since whenever you make a power series solution like this, at some point in this power series solution process, you're going to equate the coefficients of like powers of rho. In order for two power series to be equal, you have to have every coefficient in the power series be equal. So you're going to split up the overall sum into a series of equalities. That's what ended up giving us our recurrence relation when we were talking about the quantum harmonic oscillator, but I'm getting ahead of myself. This is our expression for the first derivative of our power series for v of rho differentiated with respect to rho. If I repeat this process again, taking the second derivative of v with respect to rho, I'm going to work with this power series now. Again, I'm going to end up with the sum from j equals 0 to infinity. Working with this, I've got a j plus 1 from before, and then I'm going to bring down a j, and I'm going to still have my c j plus 1, and I'm going to end up with rho to the j minus 1 as the power here. I will not actually have to relabel the indices in this sum, since the only place the second derivative appears is multiplied by rho. So if I end up distributing this rho into the sum, I'll end up with a rho to the j. So let's actually see how that works out. My left-hand side of this power series expression now becomes rho times my second derivative of v with respect to rho, which is a sum, j goes from 0 to infinity, of j plus 1 times j times c to the j plus 1 times rho to the j minus 1. Just copying this expression for the second derivative in. The next term here has to be broken up into two pieces if I'm going to want to equate like powers of rho, because I have here rho to the 0 and here rho to the 1. So for the 2 times the quantity L plus 1 part of the first partial derivative of v term, I'm going to use my relabeled expression, the one with rho to the j in it straight. That will give me, after I've multiplied everything into the power series, a rho to the j power. So I've got a plus 2 L plus 1, and that's it. That's all that doesn't have a rho in it, multiplied by the expression for the first derivative of v with respect to rho. Sum from j equals 0 to infinity of j plus 1 c to the j, c sub j plus 1 times rho to the j. That's what we want. We still have to work with this minus 2 rho times the first derivative of v with respect to rho term. And for that, I've got minus 2 times rho, and for this I'm going to use the power series for the first derivative of v that has a rho to the j minus 1, since I'm going to be multiplying in a rho, and I want in the end everything to be raised to the j power, or the rhos to be raised to the j power. So, substituting that expression in, sum from j equals 0 to infinity of j c sub j rho to the j minus 1 power, copying this in. Finally, I've got this term multiplied by my power series of j, and I don't have to do anything fancy for that. I've got rho naught minus 2 L plus 1. That's it, multiplied by my power series here. Sum from j equals 0 to infinity, c sub j rho to the j. Now, all of this is my left-hand side expressed in terms of power series, so this is all going to be equal to 0. So this is my power series representation of my differential equation. Since what I'm looking for is a power series solution, in order for this equality to hold, this polynomial, all the coefficients in this polynomial must be 0. So the coefficient of rho to the 0th power is going to be 0, coefficient of rho to the first power is going to be 0, etc. And since I can multiply this rho into this and get a rho to the j power here, likewise, I can multiply this rho in and get a rho to the j power here. The coefficients that appear in these sums are all already lined up. So if I take the j equals 0 term from each of these sums, I'll get a valid equation. if I take the j equals 1 term from all of these sums, I'll get a valid equation. This effort with relabeling indices was essentially to get all of these sums to line up. Pardon. So when I do that, when I equate coefficients, I no longer have any sums, and I just have j plus 1 times c to the j plus 1, no more rows either, plus 2l plus 1 times j plus 1, c to the j plus 1, minus 2 times j times c to the c sub j from this, plus this, rho naught minus 2l plus 1 times cj. And that all has to be equal to 0. This expression is actually something that we can work with reasonably easily. And I'm going to attempt to move it up to get myself a little more space to work with on the bottom here. Apologies for making the slide look cramped. But we have a c sub j plus 1 there and a c sub j plus 1 there. We have a c sub j there and a c sub j there. So I'm going to move the c sub j terms to the other side of the equation and factor out the c sub j. I'm going to factor out the c sub j from these two terms, leaving me with just these coefficients, the j plus 1 and the 2l plus 1 j plus 1. And I'm going to divide through by those coefficients. And what I do, or what I get when I do that, is that c sub j plus 1 is equal to j plus l plus 1 minus rho naught divided by j plus 1 times j plus 2l plus 2. You can factor out a j plus 1 from both of these terms, so that's where this factorization comes from, multiplied by c sub j. And this is something that we can really work with in the context of power series. This is a recurrence relation that if I tell you c sub j tells you c sub j plus 1. So if I tell you c sub 0, for instance, the coefficient that's multiplied by rho to the 0th power in my power series representation of v of rho, that will tell me c of 1. Knowing c of 1, I can find c of 2. Knowing c of 2, I find c of 3, etc. If you remember back when we were treating the quantum harmonic oscillator with power series, the quantum harmonic oscillator power series gave us a recurrence relation that told you c sub j plus 2 in terms of c sub j, not c sub j plus 1. And then we ended up with a power series composed of even powers of rho and a power series composed of odd powers of rho. And we had to separate those two. We don't actually have that in this circumstance, so this is actually a little bit nicer to work with. So this is our recurrence relation. Let's see what it does. The power series coefficients here, we're working with things that look like this. So it's useful to figure out what this is going to look like, because in theory, our power series might not terminate. And if it doesn't terminate, we may have problems with convergence. So let's examine what happens for very large powers. Large powers in this context mean large values of j. And if I make a large j approximation here, I have a j in the numerator and a j squared in the denominator, effectively. So what I'm going to end up with is something like c sub j plus 1 is approximately equal to, for very large j, 2 over j plus 1 times cj. What this actually ends up giving you is, for instance, let's consider what I would get for c sub j plus 2. C sub j plus 2 would be, this 2 is going to reappear and going to end up with 2 squared j plus 1, sorry for the mess, j plus 1, j plus 2, c sub j. So if this were the exact recurrence relationship that we had to work with, we would end up with something that's starting to look like the factorial here and starting to look like the nth power of 2 in the numerator. So we would end up with, for a large j approximation, something like c sub j is approximately equal to 2 to the j power over j factorial, all multiplied by our original c naught. So if this is the form of the coefficients of our power series, this should look familiar. This means that v of rho is approximately equal to, for large rho, c naught times the sum from j equals 0 to infinity. Assuming this is exact, we can start our sum at 0. 2 to the j over j factorial. It's not 2j, it's 2 raised to the jth power, times rho to the j. That's our representation of v of rho. And this power series should look familiar to you. This is c naught times e to the 2 rho. If you calculate the power series coefficients of e to the 2 rho, this is 2 rho to the jth power over j factorial. So x to the j over j factorial, that should speak exponential to you in the context of power series. This, however, should look familiar. What this means is that u of rho is equal to our c naught, rho to the L plus 1, e to the minus rho, e to the 2 rho. This was what we factored out before we made our power series approximation, our asymptotic forms, and now we've got e to the 2 rho back. So this is just going to give us e to the rho. This is in some sense expected, since we knew that we had an e to the rho sort of asymptotic behavior that we ruled out originally because it was not physically reasonable. So since we ruled that out as not physically reasonable, we have to also rule out this large j approximation as not physically reasonable. This is a valid solution to the differential equation, but it's not a valid physical anything, really, since it's blowing up for very large r. It's not going to be square integrable. This is not a valid solution. What this means, our assumption that there is a very, very large j that we can use to make these sorts of approximations, to make these plausibility arguments for blowing up. If there is no very large j in our sum, what that means is that our power series must terminate. So once again, the fact that this blows up means that the power series has to have some maximum power. It has to terminate. So what does it mean for this power series to terminate? It means much the same thing as when our power series for the quantum harmonic oscillator had to terminate. We had the same sort of problem. If the power series didn't terminate, things would blow up. So the fact that this power series terminates is going to give us the same sort of phenomenon as we saw in the quantum harmonic oscillator. It's going to give us quantization. What does termination look like for this power series? Well, it means that there's going to be some c, and I'll say j max plus 1. The power series coefficient 1 higher than the maximum power of j is going to be equal to 0. Once that's true, all the subsequent even higher powers still are also going to be 0, since c sub j max plus 2 is just given in terms of c sub j max plus 1. In order to have c sub j max plus 1 be equal to 0, I must have the right-hand side of this equation equal to 0. The only way the right-hand side of this equation can be equal to 0 if c sub j is not 0 is for the numerator of this equation to be 0. So that means I must have 2 times the quantity j max plus L plus 1 minus rho naught is equal to 0. Conventionally speaking, the quantity in brackets here is called n max, or just n. And what this equation then tells us is that rho naught is equal to 2n. Rho naught, however, was a constant. We defined it to be m naught e squared, I don't know where the naught came from, m e squared over 2 pi epsilon naught h bar squared k, where k was a constant we defined as usual to be k squared to be minus 2m e over h bar squared. If you combine all of these constants together, I now know rho naught is going to be 2n. So 2n is equal to this, and I can substitute in the definition of k to get my energy into this equation. I have an equation with nothing but physical constants, the energy, and an integer in it. And of course here has to be an integer since we're terminating our power series at an integer power. What that means, after you solve all this equation, solve these equations for E, since E is really the interesting relevant physical parameter, it tells you that the energy is minus, and I'll write this in the traditional way, m over 2 h bar squared times E squared over 4 pi epsilon naught, quantity squared, 1 over n squared. This tells you the allowed energies of the hydrogen atom, essentially. So this is actually a really important formula since it tells you about the properties of something that actually exists in nature, unlike quantum harmonic oscillators and particles in one-dimensional boxes. These polynomials that we get that have these properties, namely it obeys this recurrence relation, solves the differential equation we started with, and terminates, are called associated Laguerre polynomials, and they have the same sort of special function type properties that we've been working with when we were working with sines and cosines, and the Bessel functions and the associated the spherical Bessel functions and the spherical Neumann functions. Those special functions all had special properties. Associated Laguerre polynomials are no exception. They are defined in terms of the Laguerre polynomials as the associated Laguerre polynomial subscript q minus p superscript p is it's a function of x, and it's defined more or less by -1 to the p times the pth derivative with respect to x of the qth order Laguerre polynomial. So these L sub q's are called Laguerre polynomials. Not associated, just original Laguerre polynomials. And they essentially tell us what our radial wave function is going to look like. So these L sub q's are something that you can look up in the book. These L sub q minus p superscript p functions are again things that you can look up either in mathematical tables like Abramowitz and Stegen, or in the textbook, or online, or with any computer algebra software package worth its salt. But what these essentially tell us is the shape, and we can use them to calculate actual radial wave functions. Here are the first few, which are again the sort of thing that you can copy from the textbook. These have now been properly normalized, so there's a normalization coefficient out front. And I just want to point out a few patterns that you should observe in radial wave functions. So if you're trying to calculate radial wave functions and they don't obey these patterns, worry a little bit. First of all, notice that each of these has an a to the -3/2 power. The a here is defined to be, this is another one of those constants that shows up, 4 pi epsilon naught h bar squared over m e squared. This is a length, and it's called the Bohr radius, named of course for Niels Bohr. So this length tells you roughly the size of the radial wave function. It's appearing to the -3/2 power in all of these, more or less as part of the normalization constant. If a is smaller, you want your radial wave function to be larger, since you still need to cram all of that probability into a smaller space. You'll notice the next feature after this a to the -3/2 power, for instance here, or here, or here, is a polynomial in the variable r over a. So r over a is essentially the distance from the nucleus in units of the Bohr radius. After that polynomial, which you get of course from the associated Laguerre polynomials, you see an exponential. This is the exponential that we factored out originally, appearing once more. And it appears with 2 in it if I have 2 for that integer that was associated with my energy. It appears with 3 next to it if that integer that I chose for my energy, the n in the r sub nl here, is 3. What this tells you is that the larger the n, the larger the energy relative to the lowest energy state, and the larger the energy with respect to the lowest energy state, the slower the exponential decay is. Just to make sure the notation here is clear, this, for instance, is e to the minus r divided by 3a. So the r is divided by both the 3 and the a. So, normalization constant, a raised to the -3/2 power, an exponential in e to the minus r over a multiplied by some integer, where that integer is the same as the integer that you chose when you were determining the energy, and a polynomial in the variable r over a. So these are what your radial wave functions should look like in the mathematical context, and in the physical context, they look like this. These are difficult to plot because They both shoot up to large values, but I should emphasize that none of these are divergent. We removed all of the possible divergences in our factorization of our asymptotic solutions. The wave functions that diverge as r goes to 0 are not physically reasonable, since, well, infinite wave function is going to cause problems when you start calculating expected values of momentum and expected values of energy, if for no other reason than that. So if I continue this plot, this guy actually does reach the axis at a finite value. At about 3, it just doesn't show up very well on this plot. So if I look at R10, that's the red curve here, it just decreases exponentially. That was our term with, there was no meaningful Laguerre, associated Laguerre polynomial. There was only a normalization constant and an exponential. If I look at R20, that's the orange curve, now we have a slightly non-trivial polynomial. So we start off positive, this actually hits the axis here, start off positive, crosses the axis, goes negative, and then comes back. All of these things are exponentially approaching 0 as you go to very large values of the Bohr radius. And they have most of their support near the center. If I look at R30, that's the green curve, it hits the axis here. One of the patterns that you should notice is that if there's a 0 for the value of L, R10, R20, R30, the wave function is non-zero at the center. Whereas if there's a non-zero value for L, that's the second number here, for L equals 1 here, L equals 1 here, L equals 2 here, for the yellow, blue, and purple curves, the wave function goes to 0 at the center. And that should be unsurprising because the centrifugal term in our effective potential for our radial function, that was the term that looked like L times L plus 1 over R squared in our original radial equation after we'd done separation of variables and made our substitution. This, if L is non-zero, contributes a very large energy for radii that go to 0, which means the particle is unlikely to be found at that region with extraordinarily high energy. So the wave function essentially has to go to 0, since the potential, or the effective potential in this case, is going to 0, or is going to infinity, if we have non-zero values of L. So there's obviously a lot of complicated mathematics going on. The radial wave functions themselves are quite complicated, and we will spend quite a bit of time working with these functions and visualizing them and understanding what the spatial and angular structure of these hydrogen orbitals is. We'll also, of course, discuss what predictions we can make about the behavior of the hydrogen atom from, for instance, the formula that we got for the energy of the bound state for this for this particular radial wave function, for instance. Each of these radial wave functions has a different energy, and each radial wave function is going to have a different allowed set of spherical harmonics to actually give you what the hydrogen atom wave function looks like. And if you've ever seen pictures of hydrogen atom wave functions, you know they're rather complicated. At any rate, I think that's enough for now. To check your understanding, here are a couple of questions just breaking into the derivation process of the radial wave function and trying to explain in your own words why each of these features is true of the radial wave function.